Okay, so this is, I guess, part 6, I'm guessing. Anyway, this is again going to be a pretty short stream. Um, and yeah, I have been caught up with a couple of other things, so I couldn't push these out much earlier. But the the basic model is coming along pretty well, and I think we're at a point where we can pretty much at least take the encoder part of the um, transformer and sort of do at least basic stuff like I'm guessing some sort of classification can be done. If you combine the encoder decoder, you can do a lot more. That's where the generative portion can come into the picture. But yeah, I think we're getting into that place. And I'd say that, learned quite a bit. It's interesting. There's just a lot of data flowing through, a lot of floating points. That's it. Yeah. So with that, let me just get quickly into this. So today we're going to talk about one. So we've pretty much covered all of the. Sorry, let me actually change this to. Sorry, yeah, should be dark mode. Okay, so we've pretty much covered most of the architecture. That is, if you see this, we looked at the input embedding block, the positional encodings. We've looked at the multi-hit attention block. We've also looked at the add and norm layer, which is the layer normalization part, and the feed forward layer. So these are all the individual blocks that sort of make up the encoder. Also, they make up the decoder as well. But uh, we basically now need to connect all of them. Um, but before we do that, there's one piece that's actually not uh, visible if you just look at look at this diagram. That one is where you see that there's one skip connection. So there's one layer where your tensor, that's the encoder input, sort of goes directly to the add norm layer, and the output of the previous layer, which is the multi-hit attention block, is passed on to the add-on layer. So both those are combined, and then whatever comes out of that goes to the next layer, which is the feed-forward layer. Now that's usually referred to as the residual layer. And why do we need that? The reason is the key idea is that is to allow outputs of a layer to skip one or more layers, as we saw. Um, and the reason this is being done is because you have this problem of vanishing and exploding gradients. We'll get to the back propagation part. We're going through the forward, you know, the forward phase. We'll get to the back propagation phase where we go backwards once we compute, prediction and the loss, and then we want to go backwards and adjust all the weights by computing the gradients and all that stuff. So that's where this problem comes up. You can either have really small or really large gradients, and that can make training very difficult to deal with because you can't really have large numbers or very small numbers, and then in your calculations, that's going to become difficult to represent them and to compute using your classical computers. So that's kind of why we need this layer. And again, sticking to what we do mostly, we are learning not the transformer architecture. There's a whole bunch of literature out there that you can consume, and it's actually much better. I'm focused on the Candle ML framework and how this is, how you can think about it, think about this stuff being implemented using the Candle ML framework in Rust specifically. So let's look at that. The implementation is quite simple. By the way, just to sort of help folks. So the source folder, we've got pretty much most of them here, the embeddings, the feed forward, layer normalization, multi-head, all of this stuff is there. We now have residual layers, which is what we're going to be looking at. So effectively, if you just look at this, we've got two things. Just look at the architecture. You got two inputs, you can say that way. One's like a skip after you combine both the positional encoding and the input embeddings. And then the other one is whatever was produced by multi-head. Likewise, the feed forward block is also wrapped in this you can say, in this residual layer. So after each um, significantly useful layer, you do have this residual layer, just so that you don't have that problem that we talked about, which is the exploding gradients and or diminishing gradients or whatever that's called. So it's very simple. There's not a lot to do over here. What we're trying to do is basically um, we say that, okay, we've got a layer norm first. So I'll put that in my struct here. And there's also a dropout, which is not mentioned here, but that's actually in the paper. So we put that as well. So we got the dropout as well. Now, with both of them in place, uh, by the way, just to sort of recap on the dropout part, I think we discussed the dropout quite a bit. Effectively, a dropout is nothing more than you simply going to just randomly set a bunch of weights or parameters to zero because you don't want them to be affecting different parts of uh, your entire operation. And these dropouts can be applied at the attentions phase, at the feed forward layer, when you're creating your embeddings, all of that stuff. I think we sort of covered this in one of the previous videos, so I won't go into too much of that. But technically, those are the two things that you have. The layer normalization is the one that we've already uh, sort of described or defined. It's again nothing more. You already have a layer norm. I wrapped around it and sort of used it as such, just so that I understand this. That's predominantly why we're doing that. Uh, and then dropout is what dropout is. So you can create a new residual connection. But now, when you actually want to go forward, that means when you want to go in the forward phase, you want to take, if you look at the diagram again, you got your add and norm, you get this input, and then you get whatever this layer is. Now, the interesting thing is this is Rust, so we can do something like this. We can just say any sublayer that implements this trait called is residual layer input. I'll go ahead and take it as one of the inputs to the residual connection block so that we can just go forward. And that's kind of what's happening here. So the tensor that we receive, this XF, is generally what we've already gotten from the encoder input. We've got that. So we normalize that. That's our tensor. And then whatever we get from the previous layer, which is, we do all this, we basically call the forward method of the previous layer, get whatever we need to get, and then move forward. And that's how we can add, and then finally we just go ahead and add this. So I wanted to talk about that. If you look at the wording for this, in the transformer architecture, residual connections are used around each sublayer, namely the multi-head attention block and the feed-forward block. The residual connection, so the input to each sublayer is added to its output before being passed on to the next sublayer. That's essentially what is being implemented here. All right. So there's not much to talk about here. It's kind of straightforward. That's why we need the residual layer and how you can implement this. One of the interesting things that I'm yet to figure out is so dropouts can definitely be learnable. I'm just marking this as not. I mean, I don't want to learn this, is what I'm saying. So there's not a lot of stuff here. We can sort of move on to the next. The next one is going to be the encoder part, wherein I'm going to be talking about this entire block. Okay. So this block is actually repeated n times, and whatever comes out on the nth iteration is what gets passed on to this decoder portion. All right, so we go ahead and implement that. So first we'll just implement the encoder block once, and then we'll multiply that n times, or rather, we go through n iterations of that. And that should give us our encoder. So as I said, we'll pretty much go ahead and try and see, once we hit the encoder itself, can we take the encoder and do something with it? Because it might take a little while to, because there's also another part called masked multi-head attention, which we've already built. We don't need to worry about it. But yeah, just so that, we know how the encoder works. So let's look at that. Maybe just the encoder only model, we'll start with that, or we'll move to the next one. Anyways, so that's where we are. Cool. As I said, the model's coming along pretty well. There's just that I need a lot more time to do this stuff. Okay, great. So